Tabletop quantum experiment could detect gravitational waves. Predicted by Einstein's general theory of relativity, gravitational waves or ripples in space-time generated by certain movements of massive objects. They are important to study because they allow us to detect events in the universe that would otherwise leave little or no observable light, like black hole collisions. In 2015, the Laser Interferometer Gravitational Wave Observatory, simply we call LIGO, again I am saying Laser Interferometer Gravitational Wave Observatory, simply LIGO, and the Virgo collaborations made the first direct observation of gravitational waves. The waves were emitted from a 1.3 billion year old collision between two supermassive black holes and were detected using 4 km long optical interferometers as the event caused ripples in the Earth's space-time. Researchers from UCL, University of Groningen and University of Warwick propose a detector based on quantum technology that is 4,000 times smaller than the detectors currently in use and could detect mid-frequency gravitational waves. Quantum mechanics allows for an object, however big, to be spatially delocalized in two different places at once, despite being counterintuitive and in direct conflict with our everyday experience. The superposition principle of quantum mechanics has been experimentally verified using neutrons, electrons, ions, and molecules. Corresponding author Rein Marson, UCL Physics and Astronomy and UCLQ said quantum gravitational sensors already exist using the superposition principle. These sensors are used to measure Newtonian gravity and make for incredibly accurate measurement devices. The quantum masses used by current quantum gravitational sensors are much smaller, such as atoms, but experimental work is progressing the new interferometry techniques needed to make our device work to study gravitational waves. They found that their detector could explore a different range of frequencies of gravitational waves compared to LIGO. These frequencies might only be available if scientists build large detectors in space with baselines that are hundreds of thousands of kilometers in size. The team envisioned that their proposed smaller detector could be used to build a network of detectors that would be capable of picking out gravitational wave signals from background noise. This network would also be potentially useful, giving precise information on the location of the objects that are creating the gravitational waves. Co-author professor said, while the sensor they have proposed is ambitious in its scope, there does not appear to be any fundamental or insurmountable obstacle to its creation using current and near future technologies. All the technical elements to make this detector have been individually realized in different experiments around the world. The forces required, the quality of the vacuum required, the method to place the crystals in superposition. The difficulty will come in putting it all together and making sure the superposition stays intact. Rein Marson said, indeed, their initial ambition was to develop the device to explore non-classical gravity. But since it would be a considerable effort to realize such a device, they thought it was really important to examine the efficacy of such a device also for measuring very weak classical gravity such as gravitational waves, and found out that it is promising. Thank you.